Purushottam and Dr. J. Rao, dignitaries, my colleagues from various institutions, students, and participants who are present in this program. We once again welcome you all for today's webinar on current research in material science. In this webinar, we have two speakers. First speaker is Dr. Y. Purushottam, scientist, CMET, Hyderabad. Will deliver a talk on studies on microbial sintering and comparison with conventional sintering. And second speaker, Dr. Narsingh Rao, Professor and Dean, Research and Development, MLRITM, Hyderabad, will deliver a talk on design of novel materials and desired structures and properties. Material science is the subject of design and discovery of new materials, in particularly solids. Materials are metals, semiconductors, ceramics, polymers, etc. So material scientists generally emphasize the history of materials processing, its structures, and the materials properties and its performance. In the current scenario is advanced understanding in a variety of materials, particularly in nanoform, and its merits for technology applications. So I am eagerly waiting for today's talk. I'm sure that everyone will enjoy and be excited by today's presentation on microwave sintering and comparison with conventional sintering, and also design of a new materials with desired structure and properties. Once again, I welcome you all. I thank one and all.
Thank you very much, sir. Now I invite and take opportunity to invite our principal ma'am, Dr. M. Noorjahan ma'am, University College, Palamuru University, to address the gathering.
Thank you, Arjun, for inviting, and thank you, Dr. Jaypal Reddy Garu, for inviting me. Good morning, everybody. I welcome on behalf of Palamuru University to this national webinar on material science. And I just want to congratulate Dr. Jaypal Reddy Garu, the convener of this webinar, for wonderful organizing the team based on research. Actually, we had in the last couple of days back, we had mainly on the techniques, analytical techniques in detail with the principal concepts and applications. And now we are concentrating on the research side of material science. So it was a good choice of the topics. And on behalf of Palamuru University, I welcome the speakers and I thank them for sparing their valuable time and sharing their knowledge with us. Dr. Purushottam Reddy Garu and Dr. Another person from the college. So, and once again, I welcome all the participants, research scholars, and the students to this webinar and hope, as the convener has said, the material science is nowadays based on the nanotechnology is a fast growing research area, and there is a larger scope for everybody to have a research in this area, because day by day our requirements are increasing and we are at the verge of improving our own technologies. So every day a new innovation is required, and even the government is insisting on the innovations of new technologies, new materials for facing whatever the requirements to meet the challenges of a future coming and present scenario also. And they are funding really now the government has maybe it is really it should be serious enough to have a funding, more funding in the research area, because what we are seeing in India is less of funding to the research. So now it is much required, because we want to have a nearby Swayam Samruddhi and self make India and whatever the slogans which were given by the government. So I think all the funding should be increased and should encourage the new entrepreneurs or new research scholars or the budding scientists so that they can put their ideas and materialize it, because we are just stopping at the bench top, but nothing is going into the industry or application oriented. So that must be should be the aim of every research, because we are just introducing the ideas into the field, but it should be come into the application oriented. That should be the main aim, should be for every Indian and for every scientist and for every research scholar. So I welcome, I think this webinar will learn some more insights into the present topics, and really it is going to help us. And I congratulate the organizers for the successful organizing this webinar. Thank you very much, everybody. Thank you.
Thank you very much, ma'am, for addressing in this webinar, ma'am. Now I request our OSD to VC sir, Dadireddy Madhusudan Reddy sir, to address the gathering, sir. Sir may not come on video, sir. The battery is very low. Sir will be unmuting himself and he is going to speak it. Thank you, sir. Sir, I think
Hello.
even our audio is also not audible, it seems, sir.
Now it's audible. Hello.
Sir is there, sir. I'm going to unmute, sir.
Hello.
Sir,
Am I audible, sir?
audible, sir. Audible, sir.
Thank you, Arjun, sir.
Yes, sir.
Yeah. Good morning, everyone. On behalf of our Honorable Vice Chancellor, Sri Rahul Bajja IAS, Registrar Professor Pindi Pawan Kumar Garu, and on my behalf, I welcome you all to this one-day webinar conducted by Department of Physics on current research in material sciences. I congratulate the team led by Dr. Jayapal Reddy Garu, who is our Dean Student Affairs and Head Department of Physics, for meticulously planning this webinar, which is need of the hour. Even like through our university, actually, from past 2 months, we are seriously conducting webinars in various departments, where students who are situated away from physical classrooms, they are getting benefited, and not only students, even research scholars and even faculty members. In this regard, even Department of Physics have planned a series of webinars, where today eminent speakers from various reputed Hyderabad institutes, they have come forward to deliver lectures. I really congratulate the team, and I wish them all the best. Thank you, sir.
Thank you.
Sir, thank you very much, sir. Now I request Dr. M. Jayapal Reddy, sir, convener and head Department of Physics, to convene the further proceedings, sir. Thank you.
Okay. Now I request Dr. Ankam Bhaskar introduce the first speaker, Dr. Y. Purushottam. Now over to Dr. Ankam Bhaskar.
Good morning to all participants. Good morning to all participants. It's a great pleasure for me to introduce one of our speaker, Dr. Y. Purushottam Garu, who is going to deliver lecture to us about studies on microsintering and comparison with conventional sintering. Sintering process plays a very crucial role for compacting and forming a solid mass of material. There are several sintering methods, such as a conventional sintering, spark plasma, laser sintering, field assisted sintering, and microsintering. Nowadays, microsintering technique has been paid a great attention by researchers because it exhibits several features such as consuming electric power, space, saving time, and eco-friendly. Moreover, microsintering specimen exhibits better properties than those of conventional sintering specimen. Our speaker is having a vast knowledge on this topic. He is working as a scientist in Center for Materials for Electronic Technology. He is finished his MSc in 1991 at Kakatiya University, PhD in 1996 at Department of Physics, Usmania University, Hyderabad. He is obtained CSR, SRF, Research Associate, and Bioscat Fellowships. He is joined as a scientist in CMIT in 1998. He is visited as a visiting scientist in Pennsylvania State University, USA. He is expert in various research fields such as ceramic materials, synthesis of nanomaterials, magnetic materials, ferroelectric materials, and dielectric materials. He has published more than 70 articles in various international journals. H-index is 11, I-10 index is 12. He has completed 10 projects and ongoing 2 projects. All participants, please join me in welcoming to Y. Purushottam Garu. Thank you. Sir. Over to Purushottam Garu.
My slides are visible?
Yes, sir.
Okay. So, good morning to everyone. Thanks to Jaypal Reddy and team members for giving me this opportunity. And now Dr. Ankamaskar almost covered my lecture in brief introduction. So, whatever he told, I'm going to repeat the same thing. So, my name is Purushottam, and is it audible?
Yes, sir. Audible, sir.
Okay, clear. Okay, fine. So, working as a scientist at CMET in Cherlapalli, located in Cherlapalli in Hyderabad. And in this presentation, we will discuss briefly about our organization because some of the students may not be knowing, and what type of research and development activities are going on. Then, coming to the today's topic, that sintering. Just now, Bhaskar covered. So sintering and types of sintering, micro sintering. So advantages. Only he didn't told about advantages. Otherwise, the remaining 3 parts he already told. So then, in view of that one, we established one micro sintering furnace through one DST project, and able to sinter different types of materials. Then properties also characterized by different methods, and we are going to compare with the conventional sintering. So this is the outline of today's presentation. And CMET came into existence from 8th March 1990. That time it was a Department of Electronics. Now it is Ministry of Electronics and Information Technology, MIT, Government of India. With this, these are the 3 main objectives: to establish the technology up to pilot scale for a range of materials, electronic materials, and transfer the same to the industry for commercialization, to undertake applied research activities in the area of its operation, then to undertake applied research activities in the area of its operation, and to establish relevant materials characterization facilities. And we are working in a project mode. Different types of projects we are taking as per the requirement driven research we are doing. And sponsored grant in aid projects from government and as well as private also. And we have a few success stories. And this is the table which indicates the institutions in India working on electronic materials and devices. And Hyderabad has been identified as a high purity materials lab in the country. And this is slide is exclusively for the students because we have different projects are there. For time bound projects will be there, and there different types of requirement will be there. And like this, from diploma to PhD level, there is a opportunity will come. So my suggestion to the students is that visit our website time to time, make it a habit to see the government website, because now, because of this COVID-19 situation, now hard advertisements will come only in their websites. So you have to see make it a habituate to see the government laboratories website, so that one can apply. So these are the different qualifications, different positions are there. Even after PhD also one can do research associate. And this is the CMET. We have 3 laboratories: Pune and Thrissur and Hyderabad. And our registered office is at New Delhi, MIT, Ministry of Electronics and Information Technology. And 3 laboratories are working in 3 different areas. So Pune laboratory is working in the processing of thick film materials and chemicals, and their thrust areas are electronic packaging materials, sensors, optoelectronic materials. Coming to Thrissur, they are working on high-tech electro-ceramic materials, multi-layer ceramics, multi-layer actuators, micro substrates. Then Hyderabad laboratory is core competence is ultra purification of different materials and high purity metals and alloys, refractory metals, compound semiconductors, e-waste, electronic waste, ROHS testing and certification. These are our R&D activities. So far we developed the process technology for the ultra high pure metals of these 3 tellurium cadmium from ore. So these 3 metals are there: tantalum, niobium and hafnium. Further discussion on the high purity, you see now this table gives the purity level. 99.9% is nothing but 3 nines, that is with the impurity. And if you convert into percentage into ppm level, that will be the 1000 ppm. So some of the properties where the impurities are playing major role in the compound semiconductors, optoelectronic applications, type of devices, this starting material should be of ultra high pure. So in that case, one has to develop the technology to obtain the ultra high pure materials. So CMET Hyderabad is involved in this purification technology, and our concentration is only on impurities. From 1000 ppm to we develop the process technology up to 0.1 ppm. So as the N goes, yes, this is the like this 3N, 4N, 5N, 6N, 7N. So this 6N or 7N, they are call it as a ultra high pure materials. And if you take any metal of this 3N metal and 7N metal, there is a lot of value addition will be there. If this metal is available, for example, a few hundreds of rupees, for example, in the case of zinc, this is a per kg 300 rupees, whereas this is a 7N will be 1 lakh. So such a value addition will be there, and requirement is also very specific requirement. So in the country, around 50 to 60 kg of metal is enough for the strategic applications, DRDO, atomic and nuclear applications, space applications. So we are developing different materials now. Right now, two projects are under. I am handling 2 projects: germanium purification and zinc purification. We are purified up to 0.1 7N pure. This one 7N purity metals, and we are supplying to the this collaborative laboratories. So here, just this is a textbook information. Purification means it has to convert from the one form to the other one, phase to the other. So solid to liquid, liquid to gas, or gas to solid. These are the various well-known purification processes. Whereas economically viable technologies is distillation and zone refining. We are doing the first. We are doing the distillation process, then followed by zone refining. So this is the way. Starting material will be of 3N, any material metal. So that we are by distillation process, vacuum distillation process, it will be of 5N. Then that 5N material will be loaded for the further purification. That is a process called zone refining. And then we will get the 7N pure, 99.59. So this there is a two, ICP-MS and GD-MS. These are the characterization equipment to certify the impurities, elemental impurities analysis. And there are two physical properties are there, vapor pressure and distribution coefficient of the impurities. This is the graph, gives the vapor pressure and distribution coefficient of different materials which are available in is there. And depending upon the high vapor pressure will be removed first in the vacuum distillation. Then the target material and surroundings will be in the residue. Then in the second distillation, the target material will be removed out. So in this way, after that one, this zone refining, distribution coefficient which is less than 1 will be removed easily. So in this way, majority of the impurities will be removed by zone refining technique. Another important societal applications activities in our laboratory is that the electronic waste, environmentally sound methods for the recovery of precious metals from the PCBs, printed circuit boards. As we know, PCBs are everywhere on electronic gadgets. PCB will be there. That is nothing but this is a motherboard. If you take any high-tech electronic gadgets like a laptop, desktop, and mobile phones, all this is a motherboard is the only one of the important parameter. So in this one, if you take any motherboard, number of components is there. Now because of this technology evolution, lot of new gadgets are coming every day into the market, and old gadgets we are simply keeping or throwing out. So in this way, hundreds of tons of e-waste is generating in the country every day, like municipal waste. So this we Government of India had identified our laboratory and given a project to extract the precious metals from these PCBs. This PCB, if you take, for example, this is the composition of the PCB, that if 70% will be of the polymers only, glass reinforced polymers, and 16% of, you take one PCB, 16% will be copper, then 3% is iron, then 2% nickel, 0.05 is the silver, 0.03 palladium, and 0.03 gold. So if you take one PCB, these three metals are very minimal. It will be in the milligrams only. But if you take some 1 ton or 10 tons of PCB, then we cannot neglect these three precious metals. Substantial amount of precious metals can be obtained. So now we, in the CMET Hyderabad, we developed the process technology, and first we are taking the e-waste, whatever the e-waste, then physical separation. By physical separation, one can segregate the components which can be reused, and then only this mother PCB will come. And in this PCB also there are several components are embedded, resistors, capacitors, ICs, so many will be there. Again, they can, after desoldering, they can reuse. So if you take one PCB, all these things are nothing. But if you take 10 tons or 20 tons, then all components, all resistors, all capacitors, after soldering the solder material itself, that lead itself is a substantial quantity will be there. Everything will be recycled and reused. Now that is the circular economy. Now all entire research is going on towards the circular economy, because we cannot discard this e-waste forever. So we developed the process technology, and developed the process technology and prepared gold, silver, and palladium. These are the three precious metals, and we transferred the technology also to one industry for commercialization. This is the process flow chart what we developed. So from the PCB, we have a collaboration with one industry called E-Parisara in Bangalore. So they are giving the only PCBs. Before that one, they have a very huge facility. Around 400 employees are there. They are segregating the e-waste by physical methods, and they are giving only these PCBs. So then there are the processes are there, that is called depopulation, calcination, smelting, and electro refining, then solvent extraction. This is a hydrometallurgical operations. So finally we are getting. So now we have a 100 kg per day batch process is going on right now in our laboratory. We are enhancing this to 500 kg per day. Then we have our target is 1000 kg per day. Then only this economically viable. Otherwise, now 100 kg per day is economically not viable. But we are another major program is going on Center of Excellence. We are going to establish a Center of Excellence on e-waste management. And those who are interested, they can come to CMET and they will be trained how to e-waste dismantling and segregation is a self-employment opportunities are there. So that activity is going on. Then we are slowly one by one, all the technologies we have to transfer to the industries. Another, industry related activity is the ROHS, testing and certification. ROHS is nothing but restriction of hazardous substances. Where this electrical and electronic items, whatever manufacturers which are manufacturing and sending to different countries. So one certification is required, and these are the allowable limits. This is called ROHS regulations. There is a e-waste management rule 2016, which is effective even in our country also from 1st October 2016 for any electrical and electronics E&E items. These are the allowable limits. This is called ROHS limits. For example, in 1 kg material, lead should be 1000 milligram, cadmium should be 100 milligram, and hexavalent chromium is 1000 milligram. Then mercury 1000 milligram. So this is a PBB and PBDE. These are polybrominated biphenyls and polybrominated diphenyl ethers. This is the restriction is there. So one has to, electrical and electronic manufacturers, they have to attach. If you take any new, any cable or any electrical item, you can see there is one ROHS compliance that is where ROHS tested, that polythene cover. So we developed the process technology and certification. Our laboratory is a NABL accredited laboratory. So as per this, there is a ISO standards are there, and this is a industries, micro, small, and medium entrepreneurs, those who are difficult to establish this costly equipments. So they are taking our service, and a lot of samples are coming, and more than 200 industries where they are taking our services. So this is the so far R&D activities. Briefly I told. Now coming to the topic of today's lecture is sintering. So as Bhaskar already told, that sintering is a high temperature process where that consolidates and strengthens the loose or compacted particles in a more dense coherent body. So if we want to take any loose powder, we have to make compact, and that is called a green pellet, and it doesn't have much strength to further then we have to do sintering. And what will happen during sintering? Powder particles form coherent bonds and densify by pore shrinkage. So like this, when these loose powders, if you by applying force, it will be like this, but after sintering, it will be the form. So coherent bonds, and it will pore shrinkage. Due to pore shrinkage, it will become a high density material. So there is a different stages are there during sintering: initial particle bonding, neck growth, pore channel closure, densification or pore shrinkage, and pore worsening. If you increase the temperature, time for the sintering time, if you exposed your material for longer duration, what will happen? So this pore coarsening also will take place. So these are the some of the pictures. This is the different stages are there in this during the sintering. And there are different types of sinter reactions also there. Single component sintering of metals, oxides, and hydrides. Multiple component sintering of solid solutions, intermetallic or mechanically bonded systems. Activated sintering with additives. And these are the conditions. So those who are fresh MSc students or research scholars and scientists, whoever is there. So we are playing on these kind of parameters only. Rate of heating and cooling, centering time, centering temperature, centering atmosphere. So with this, these are the four important conditions where one can do their entire lifetime. We can spend on these by varying these different conditions, combinations, permutations, and combinations, and that is what research is going on, and we are getting very good results also. And this is now types of sintering: activated and liquid phase sintering, activated sintering, liquid phase sintering, and solid state sintering. Then in this solid state sintering, the growth of the center board form an initial loose powder compact is characterized as the initial state of sintering. In this stage, the neck size is sufficiently small that neighboring necks grow independently of one another. And this is there are two types are there: microwave sintering and laser sintering. So coming to microwave sintering, a process for heating powder materials by microwave radiation so that heating and sintering or melting progressively and directionally occurs within the powder materials. So here the volumetric heating will take place in the microwaves, and the process generally entails forming a structure from a powder by arranging the powder in a mass according to size of particles of the powder, so that the particles are progressively arranged within at least a region of the mass from smallest to largest. So this is in the whatever the material to be heated under microwave, and there these polar molecules and free ions in that material respond to these fields. What will happen? Microwaves penetrate at a speed of light, such a rapid speed, and these polar molecules and free ions which are there in this our respective material, they will create a molecular friction which results in heat throughout the mass of the material. So this is the microwave sintering of why microwave sintering is very fast, because of molecular friction. Because of molecular friction, this material will be rapid heating. Within minutes, we can reach hundreds of degrees of centigrade. And here, this microwaves are electromagnetic radiation with wavelengths ranging from about 1 mm to 1 meter in free space, with frequencies between approximately 300 gigahertz to 300 megahertz. And microwaves have a practical industrial range of between about 500 megahertz to 10 gigahertz. But only two frequencies are allowed, that is 915 megahertz and 2.45 gigahertz are permitted by regulation for industrial and scientific applications. Other frequencies are for military applications. So this is the electromagnetic spectrum. This is the gamma rays, X-rays, UV, visible light, infrared, microwave, and radio frequencies, radio waves. So this is the VIBGR, and these are the wavelengths. So here, this microwave heating is a fundamentally different from conventional heating. In conventional heating, one minute. Leave it. So microwave heating of material is fundamentally different from conventional heating. Okay. Stop sharing. Huh? What is that?
It's fine, sir.
Okay, okay. Because this is admit, always it is coming, so I am not able to read my slides.
We will do it very fast, sir. Not to appear, sir.
Okay, because every time,
Yes, sir.
so that is I am not able to read my slides.
PPT,
So
yes, sir.
I am okay. Now it is okay. So microwave heating of materials is fundamentally different from conventional radiation, conduction, or convection heating. And in this heat is generated in the microwave process. The heat is generated internally within the material instead of originating from external heating sources. So if you see the energy penetration will take place. Selective energy absorption which also takes place. Only material to be heated will be absorb microwave energy. Now you see in conventional heating is nothing but resistance heating, where this material of the target temperature will be first we heated by the heating elements, then that after reaching the target temperature, then this sample will be heated by conduction, convection, and radiation, which requires a long duration to reach the target temperature. So there, what is happening by that time, the material to be heated will be exposed for longer duration, and after reaching the set temperature in conventional sintering, again coming back to room temperature, it will take another few hours. So while starting to end the material which is unnecessarily it is exposing for longer duration, which can result some of the grain growth operations. Unless in the conventional heating, in microwave heating, the material themselves absorbs microwave energy within no time. Because here in this conventional heating, energy is transferring, whereas in microwave energy conversion, microwave energy is converting into thermal energy, whereas here it is the energy transfer, and external heating source is there, whereas here it is internal heating, and this is a material independent, whereas microwave is a totally material dependent, and there are some energy losses are there, whereas in this one highly efficient sintering, as far as sintering is concerned, that set temperature will be reached within no time. You can see here temperature time profile. In microwave heating, the same temperature, for example, 1200, set temperature is 1200. For example, if you take which can be within minutes only, you can reach 1200. Whereas in conventional, it will take hours together to reach the 1200. Then we have to keep for 1 or 2, 3 to 4 hours. Then only desired density or desired properties will be obtained. And again, to bring back to the room temperature, again it will take few hours. So all these things is not possible, not required in microwave sintering, because of microwave penetrates, as I told, microwave penetrates at a speed of light, and polar molecules and free ions which are there in the material to be heated, they will molecular friction will take place. As soon as we switch on the microwaves will be released by magnetron, source of magnetron, then that will penetrate through the material. So in the microwave heating, volumetric heating takes place. Only material only will be absorbs microwaves. Remaining are doesn't absorb microwave. And here energy is transferring through the electromagnetic energy is converting into thermal heating. Microwave couples with the powder particles and induces an electric field within the sample. Because of this one, we are getting a rapid temperature within no time. And there are many advantages are there. Microwave heating offers numerous advantages. So energy penetration, selective energy absorption, instantaneous electronic control, high efficiency and speed. It is a clean process and high speed. It saves a lot of space, reduces scrap and labor also. If you, in terms of industrial point of view, labor also saves. So due to that one, it is having a lot of applications, microwave processing. And here one can see microwave interaction with the material. If the material is a transparent material, depending upon the material type, if the material is a transparent material, microwave penetration will be total. If a material is a conductor, like metal, it doesn't penetrate. It will reflect back. If it is a lossy insulator, absorber type of material, from partial to total. Whereas it is a mixture also, mixed material, again it is a partial to total. So microwave heating is totally material dependent. If you take any metal, you cannot heat metal because it doesn't penetrate into the metal. And that's why research is going on in the metal powders. So my the reason what I got a DST project on establishing a micro sintering facility is that we are, in the beginning I told, refractory metals. We developed the process technology refractory metals from the ore. So that refractory metal powders, I made an attempt to whether sintering is possible or not by microwave heating, because as such metals we cannot heat. So metal powders possibilities are there. So these several advantages are there of micro sintering, and high efficiency, speed, microprocessing is very clean. And here, because of these advantages, you see a lot of applications are there, commercial and industrial applications, heating food, a micro oven. We are very well known about this oven, where this is microwaves to generate heat and warm food. So if you go to any bakery, that person will give whatever our item within minutes, because it will be a warm. Then in communications, microwaves are used to send communications signals to and from satellites. They also carry signals for mobile phones, wireless computer networks, and personal digital assistants. And this radar, radio detection and ranging, radar equipment bounces microwaves off moving objects to detect them. And in the astronomy, large microwave receivers called radio telescopes study microwaves emitted from space. And in the different industries, textile, food and paper industries, for drying clothes, potato chips, printed matter, etc. Food processing industry, rubber, plastics, chemical, forest product industry, they are using microwaves, and their microwaves are also having applications in biomedical applications are there. And this is the kitchen microwave oven, we all know. So where here this is called magnetron. This is a source of microwaves. Microwaves from there are three types of sources are there: magnetron, klystron, and garretron. So magnetron is a very coming to other. This is a cheaper. So they are all domestic microwave oven. They are having magnetrons, and this source of microwaves. These microwaves pass through the waveguide. This is called waveguide. Rectangular and circular waveguides are there. Two types are there, and from here only this after the moment if you observe, if you go to any bakery, we concentrate only on about a food whatever we ordered, but the moment if you close that one, this will start heating. So microwave source from the magnetron, it will pass through the waveguide, and that will come to the material to be heated, whether it is a whatever the material, and it will since it is a material dependent, only material only will be heating. Others doesn't take any heat. You can take it out without any problem. And So we in one or 2 minutes, whatever the set temperature you can able to get, and we can take the this warm food. So these kind of applications are, a number of applications are there. And in view of our research activity on refractory metal powders, so we established one micro sintering facility at our laboratory through a DST project. And it is and another thing is that in the domestic oven, whatever we are buying or using or seeing, where this is a 800 kilowatt oven. This is only 800 watts. 800 watts, sorry, not kilowatt, 800 watts. So this is sufficient for the domestic purpose. Whereas in our furnace, I procured 2 kilowatt chamber type micro furnace, and it consists of waveguide for the flow of microwaves, pyrometer for measuring temperature, because we cannot keep the thermocouple here. Whereas in conventional furnace, if you see, we can measure using the thermocouple what is the temperature. But you cannot keep a thermocouple in the microwave, because thermocouple is a metal. It is a combination of two metals. So since it doesn't penetrate, it will start a reflection. What will happen if you after switch on for some time, if the thermocouple is there, then that reflection will goes back to through waveguide, and it will damage the magnetron, the source of microwaves. So that kind of problem will be there. So thermocouple is difficult. So non-contact method is the optical pyrometer. So pyrometer is there for measuring the temperature, and this chamber is made up of steel, and the microwaves generates by magnetron, which works at 2.45 gigahertz frequency. As I told, there are two frequencies, so this furnace is of 2.45 gigahertz. And we can evacuate the chamber if you want to do sintering in different conditions. And as I mentioned in the beginning, 4 different types of conditions if you want to implement, then that provision is there, and cooling water circulation is there to the chamber and magnetron during the experiment, and the temperature is controlled by a PID temperature controller, and there are 4 ramp and 4 soaking facilities are also there. As per the program, one can do the sintering. So that facility is there. This is a state-of-the-art equipment, and and we can data acquisition facility is also there, so that one can review after sintering, after completion of the properties. If the properties are not as per our expectations, then we can review what are the parameters have been affected. There is a possibility to do modification, optimization of process parameters purpose. This data storage, acquired data will be used. And this is another one more viewport is also there in this one, because if you those who are regularly using resistance furnaces, conventional furnaces, we know that after putting our material inside, then we will close the door, that's all. But what is after set temperature only, external only we can see, but what is happening inside we cannot see. There is no provision. But whereas here there is a viewport, you can see the what is happening at your set temperature. And this is the pyrometer for temperature sensing, and this is the magnetron, and this is the waveguide. So from here, these microwaves will enter into this chamber. And there is a gas purging facility is also there, so that nitrogen, argon. Actually, we tried. Our aim was hydrogen, but there is a small, air leak is there between this magnetron and waveguide. So hydrogen was coming out from this gap. So due to that one, we could not do, because hydrogen is there is a chances of catching fire. So we could not do experiments with the hydrogen, but we successfully conducted with inert gas. And this is a microwave power controller, and these are the IR pyrometer and temperature. We can PID controller, we can program it. So as per our requirement, one can do sintering. And before starting that one, we have to check with a micro leak detector whether any leakages are there, because this is also microwave, exposing to microwave is for longer duration is also not good for our health. So this is a magnetron and this is a pyrometer. And these are the salient features that the micro frequency is 2.45 gigahertz. And depending upon the absorbability of the microwave, this material, microwave output power will be continuously variable from 0 to 1.95 kilowatt, because this is a 2 kilowatt furnace. So continuously variable. It is not just on off. If you see the any this domestic oven, whatever we are using, if you close the door, it will be 800 watts, and if you open, it will be 0. Whereas, so either 800 or 0. But whereas here in this our furnace, it is depending upon the penetration, depending upon the microwave's penetration, the power will vary from 0 to 1.95 kilowatt. And one can obtain 1600 degrees centigrade. So maximum temperature, but I operated up to 1500 degrees centigrade. And this is the pyrometer range from 250 to 2000, because our requirement is high temperature. There are different types of pyrometers available with adjustable emissivity. And so this is the range. Below 250, it is showing only whether it is room temperature, or 249, it will show only 250. So because of our requirement is high temperature, that's why we selected this in this range pyrometer. And this is the temperature controller is PID. And one can up to 1 kg of material also can be loaded. Such a big chamber is there. And this is the sizes, and ambient atmosphere and argon, nitrogen also there, and interfacing data equation is also there. So like this, on the screen, this Excel sheet, the data will be stored. Data means this is temperature and micro power, and whether it is we can do manually and auto mode. After entering the sintering parameters in the PID controller, if you if you want to select in auto mode, it will, as per that one, it will select. And like this, so graphs are, we get different types of materials. So temperature versus time graph, and this is the furnace. So if any was interested to do your samples sintering by microwave, and if you want to compare it to studies, so it is you are welcome. And this is a furnace. So this is totally indigenously, it is a energy micro systems. It is in Bangalore. And if any problems are there, because high temperature, we are doing all our high temperature. So if at all any problems are there, then this is a alarm will give. This is a tower lamp. So that provision is there, so that immediately we can switch off the furnace. And inside the chamber, so these are the ceramic caskets, and this is nothing but sample holders. So this is a Al2O3 alumina made ceramic cassettes. Depending upon the size of the sample, one can this is a sample holder. It is nothing but simple sample holder we can make. And in the sample holder, this is a suppose if your material is not microwave absorption is low, then bottom one can keep this susceptor. These are called susceptors. This is a silicon carbide susceptors, and silicon carbide is a very well micro absorber. So what will happen if your material, for example, if your sample is not taking heating, then if you keep below of this this susceptor, this once you switch on the microwave, this will first absorb microwave and it will convert it to heat. Then that heat will be transferred to here, and after that one it will start. If your material is not microwave absorption, otherwise this is not required. So before sintering, it will be like this. So we are loading in this way and closing the chamber door. So this is susceptor is nothing but silicon carbide made, which is absorbs microwave energy efficiently, converting it into heat, which in turn radiated back onto the sample. So ceramic casket is a low loss insulation material. And so this, as I told you, this is a very selective heating. Volumetric heating will take place. if you see this during the sintering, we took some pictures. You can see only, whereas this entire ceramic cascade, but only susceptors are heating, selective heating. If you see here also, this entire if you put in conventional, everything will be in a hot condition, whereas here only sample is in hot condition. So selective heating. And you see now here 3 different is there, before sintering and during sintering and after sintering. What happened? You see, particularly for this particular sample, this was not fully, actually it was sintered, but there is a warpage took place. Because why? Because this is due to rapid heating. There are several factors again. So rapid heating or the exposure will be longer. So again we have to optimize. We have to optimize the process parameters. This is also one of the important here. And you see, after sintering, it looks like this. This is a very clean process. So inside the chamber, it will be like this only. Whereas here, this casket, low loss insulation material, which is having some moisture. So there are different grades. Moisture is fibers also is available. So 1200 degrees centigrade, 1400, 1600 degrees centigrade. Whereas this, whatever this picture is a 1200 degrees centigrade ceramic fiber. So what happened when we started the sintering experiment, and here this moisture has come out from this fiber. So in the first sintering, it looks like this like a black color, and after 2-3 sintering experiments, this again it will come back to white color, because whatever the moisture is there, that has been removed. And after establishment of this micro furnace, variety of materials we sintered. Not only our refractory metal powders, so nickel zinc ferrites, tantalum metal powder, niobium metal powder, oxide materials, hafnium metal powder, iron oxide, so PZT, barium titanate, barium ferrite. So from our Usmania and even other are also many people utilized, and with the different sintering conditions. Many materials, still it is going on. So this is what I told. So I used this furnace up to 1500 degrees centigrade for 90 minutes, 1.5 hours, 1500 degrees centigrade. So this is the temperature versus time. And this is a tantalum pentoxide 1250 for 30 minutes. This is a PZT material, BTech students project. And this is iron oxide, again for BTech student projects, 1000 degrees centigrade for 20 minutes. This is a 1400 degrees centigrade for 30 minutes. And CMR materials, 1350. Ferroelectric materials, 1350 for 15 minutes. So like this. So after sintering, characterization, this is anyway very well-known techniques, density by Archimedes method, structural composition by XRD, microstructure by SEM, magnetic properties by vibrating sag-and-pull magnetometer, VSM. So particularly why I told about this nickel zinc ferrites, because we studied in detail this nickel zinc ferrites. This is a compositional formula, nickel 1 minus x ZnX Fe2O4, where x equal to 0 to 1 in steps of 0.2. We started using high purity nickel oxide, zinc oxide, and iron oxide. So here 2 batches of iron oxide we used, Fe2O4, Fe2O3, and Fe3O4, because we want to see the absorbability of microwaves Fe2O3 and Fe3O4. So that's why 2 types of iron oxide we used here, and we found that at 2.45 gigahertz, Fe2O3 is absorbing less microwaves compared to Fe3O4. So this is what we found. So one has to use Fe3 iron oxide means Fe3O4, and after pressing the pellets, calcined 1100 degrees centigrade for 4 hours in conventional furnace. This is not microwave. Then one batch of pellets we sintered at 1275 for 30 minutes, and same way another batch by conventional procedures for comparison purpose. This is a general definition of ferrites, because ferrites are magnetic ferromagnetic materials. This is Fe3O4, Fe2O plus, and Fe2O3, and there are number of applications are there. So the unit cell of the ferrites contains 32 oxygen ions, 16 trivalent iron ions, and divalent E cell. Depending upon the distribution of these 24, whether it is a spinel ferrites or inverse spinal ferrites, and particularly nickel zinc ferrites is having a lot of applications as a transformer cores. You see, radio frequency circuits, high quality filters, rod antennas, transformer cores, read-write heads for high digital tape, etc. So there are limited reports were there that time on a systematic studies by microwave sintered nickel zinc ferrite. That's why we took this study. So this is a XRD by conventional method. Both the type of materials, whether it is conventional or microwave, are having a spinal structure, and this is a microwave sintered XRD, and the density almost lying in the same range. So it is a both are in the same range, because 1275 for 30 minutes. And if you see the microstructure in conventionally sintered, samples had tiny pores densely distributed here in conventional, whereas in microwave sintered had bigger pores and uniformly distributed. That is what we observed. And since these are all the soft magnetic materials, coercivity will be less only. And conventional, micrographs, BH loop, hysteresis loops of this conventional and microwave sintered materials. Both types of materials are showing low coercivity only because of this soft ferrites. And saturation magnetization and coercivity versus zinc concentration has been there. And this is because of formation of uncoupled spins with increasing X value, this the coercivity is having a low value. This is another refractory metal powder, so tantalum, which is having a phase pure tantalum, and this is the microstructure of because this tantalum metal powder what we prepared is for capacitor applications. So capacitor applications, if you sintered that porous structure is required. So porous structure is required, whether we will get porous structure or not by microwaves. So we made one attempt. We got a porous structure, and when we compared with the conventional sintered and this one microwave sintered, what happened? Our electrical properties and physical properties and chemical properties are less compared to imported powder, because we did this entire experiments under inert atmosphere. Due to that one, what happened? Oxygen pickup was more compared to imported powder. So this is because of this oxygen. So DC leakage was more, and capacitance CV is more. So due to that one, we could not get desired as per our required properties. We could not get by micro sintered, but we are able to sinter the materials. This is a niobium pentoxide, phase pure, and this is a barium titanate, barium ferrites composite material. So microstructure of barium titanate, barium ferrite composites, and this is a barium ferrite. This is a DMRL samples, and you see a density, high density material. The same material of barium titanate, which we sintered at 1100 degrees centigrade for 30 minutes and 1400 degrees centigrade for 30 minutes. What is the microstructure difference? Enormous grain growth happened. You see, very clear grain boundaries we are able to see, whereas there are no much grain boundaries. So one can this kind of academic activity purpose, we can do sintering at different temperatures and different conditions. And these are the composite materials, whereas this is a barium titanate, barium ferrites, and barium ferrite by microsintering. And you see here, this hysteresis loop is very, very well in the microsintered samples because magnetic properties are more, saturation is more, and cohesivity is also more in these microsintered samples. So like this, now in the conclusions is that high temperature microsintering furnace was established at CMET, and we made it to suitable for sintering refractory metal powders. Variety of materials sintered with the different sintering conditions by applying microwave energy, and we got interesting results. And with this one, we are trying to understand the science of micromaterial interaction. So thank you for your attention. This is the end of my lecture. Hello?
Hello.
Yeah, Jayapal.
Thank you, Purushottam. Hello.
Yes, yes.
Yeah, it's a time for questioning. Hello. Hello, Arjun. Hello.
Hello, sir.
Bhaskar.
Sir, I have 3 doubts, not questions.
Tell me.
So, can I ask, sir?
Yes, yes. Why not?
Yeah. Can we use microsintering technique for mass production, sir?
Yes. It is there now. Already. This whatever the industries, whatever mentioned, they are all mass production.
And one more, sir.
Yeah.
Is it specimen uniformly sintered by microsintering technique?
Yes.
Yes.
Uniform. We got more than 97% density.
Okay. And one more, sir. How avoid hotspots during microsintering process?
Hotspots means?
Hotspots means some places materials will melt due to the high concentration of microwave penetrated those spots.
So then whatever the plate will be there, na?
Yeah. Okay.
If you see the domestic oven, the moment if you close the door, that plate will be rotating.
Yeah, sir.
So that kind of arrangement is required for uniform absorption, uniform penetration.
So one more doubt, sir. Which type of micro cavity you are using? Because multi-mode is there, single mode is there.
Multi-mode.
So
multi-mode only is a, is there.
Because multi-mode means they are not concentrated at one particular place, all microwaves. Is it true?
No. Again, it is material dependent only. Since the moment if you keep your material and once you start, the penetration, whatever the penetration, depending upon that one only. If you put a susceptors.
Yeah, sir.
So suppose if we are not able to sinter the materials properly, then what you have to do? Bottom of your material susceptor. If you keep one small pellet, small piece, that will take care.
Yeah, which are not absorbing the microwaves.
Yes. Initially.
Yeah, later on.
Once it is started heating and transferring,
up to certain temperature, then absorbing.
Then will you microwaves?
Because the electric losses.
Yes. Because so many materials we studied, so many.
Yes, sir. Yes. Thank you, sir.
Hello.
So, is it okay, my lecture?
Yeah, it's fine.
Very good.
So,
very good.
I'm expecting response from the audience.
Yeah.
So, Arjun, Anjaneyulu.
Sir, Arjun sir, technical problem to exit అయింది.
ఓకే. ఇప్పుడు అన్మ్యూట్ చేస్తే కొంచెం ఆడియన్స్ క్వశ్చన్స్ అడుగుతారు కదా.
Sir, we have 2 questions on chat box, sir.
Okay.
We have two questions in chat box, sir.
So
Read it.
the question from Umameshwar Singh are, what is the role of sintering in purification of materials, and what are the hazardous materials in e-waste?
Hazardous materials are this, as I mentioned, this, whatever I mentioned, ROHS, hazardous materials means that composition is there. So it is a plastic. 70% is plastic only,
Yeah.
particularly PCB. So that has to be properly reused.
Oh.
Okay. And what was the first question?
So 1 minute.
Micro sintering,
What is the
purification.
role of sintering in purification?
Purification. No. It is nothing but nothing. There is no, both are different. Micro sintering and purification, both are different.
Okay.
Doesn't have any role, because sintering is taking place, to, if you want a high dense material.
What is the role of sintering in purification?
Yeah. So if you want to have a high density material, then only we have to sinter.
Yes.
Purpose of the sintering is to get a high density material.
Yes.
Purification is doesn't have any sintering process at all. And only thing is that maybe what I understanding that is that to get a melting temperature, for example, during the purification, suppose if you want to purify the metal of any material, you have to go up to melting point of that material. Okay. So to reach that material, to get to that desired temperature, whether we can use microwaves. Yes, that is also there. But otherwise, this whatever we are high melting materials, instead of microwave, there is another micro induction heating is there. So induction heating is the more efficient compared to this one.
Okay.
Resistance heating. There is another one more type of energy application is there. So resistance heating, microwave heating, induction heating, there are many are there.
Yeah.
Question from A. Venkat Reddy. Can we set up industrially? If so, what would be the expected cost?
Industrially, what will be the
Expected cost.
expected cost is the issue. Now there is this whatever my furnace, whatever I showed is 10 lakhs. Okay, but whereas if you want to use this is a investment depending upon the investment only. What is the capacity your plant is planning to set up, and what material, what is the rate of that one? There is a continuously variable, that blockchain type of is there. So if you want only batch size, for example, these academic institutions or laboratories, we can use some different types of batch size operation. Batch size operation means minimum 5 to 6 lakhs. Because even
from Dr. Cherupalli, can we use this technique for the preparation of glass material also?
Glass material means, you see, because based on our friends, what we are doing, glass material means if you want to prepare a glass, you have to melt it and you have to pour it. Okay, but up to melting point you can do, but immediately you have to take it out, and that is also possible, but only one has to be practice. We have to do more experiments, because with one experiment nobody will take it out from that one, but there is no problem, because now after getting that set temperature, people are doing quenching also. Quenching directly, they are bringing back to room temperature. Instead of putting like that, if you are molten material, if you are converting into glasses, that is possible. Yes, because conventional heating, again, whatever in the beginning, whatever told now, to get that temperature, it will take time. In microwave, that problem is not there. Once you confirm that your solid material, which whatever you loaded is in molten state, immediately you can switch off, and within no time you have to convert. Otherwise, that solidification will take place there itself.
Hello.
Yeah.
Anyone from the audience? to raise the hello.
In chat box we have, sir, e-waste hub can we establish in engineering colleges?
E-waste?
Hub, sir. Hub.
E-waste hub.
Hub.
Ah.
Can we establish in engineering colleges?
Why not? Because each college is having a lot of e-waste. See, those who are not using electrical and electronic equipment, they are all e-waste only.
Yeah.
So each department, if they are having any accountability is there. Suppose your management is asking accountability, then definitely I am sure 1 or 2 tons e-waste will be there in each college.
Each college.
Each college. So actually, there is we have a limitations. We have limitations, but we want to go to different colleges also to collect that e-waste. If the management is showing interest, if they want to donate, we are ready to take up. So e-waste is not a problem. Already every house is having some at least 1 kg of e-waste.
Yeah.
And colleges definitely it will be there.
Thank you, Dr. Purushottam.
Yeah.
It's a very wonderful lecture. So you have given a lot of information to us. So now you're over to Ankam Bhaskar.
Out of thanks. Hello, Anna. Out of thanks. It is my privilege to have been asked to propose a vote of thanks. Our speaker has been taken a few examples and explained the micro-sintering versus conventional sintering. He has explained the various points, the difference between the micro-sintering and conventional sintering, and fabrication micro furnace for sintering the materials, how micro technique useful for metal powders, and he's showing some of his results which reverse that micro sintering specimen exhibits better properties than other sintering techniques because of volumetricity, high densification, improve the grain boundaries, and enhance the chemical reaction. The specimens can sintered at low temperature or low soaking time by micro sintering technique, which is suitable for fabrication of electronic device. The way in which he explained his topic was extraordinary. I'm sure that all the participants would take note of important points during his lecture. On behalf of our department and all the participants, extend a very hearty vote of thanks to Honorable Delegate who blessed us with his presence and took out valuable of his time even though he is busy. Thank you, sir.
Thank you.
Hello. Now I request Ankam Bhaskar to introduce Dr. G. Narsingh Rao. Hello, Bhaskar. Hello.
Okay, sir. Idedo start mute press sir. Good morning to all of the participants. It's great pleasure for me to introduce one of our speaker, Dr. G. Narsingh Rao Garu, who is going to deliver a lecture to us about design of novel materials with desired structure and properties. Many researchers are interested on the single crystal with polymorphism. Poly means many, morphe means shapes. The substance exists in more than one crystal phase that have different arrangement of molecules in the crystal lattice. As a result of it, this will affect on various properties. Our speaker is going to explain how single crystal with polymorphism will affect on properties such as a topological insulator, low dimensional magnetic, and superconductor properties. Our speaker is having a vast knowledge on this topic. He is working as a professor in as a professor, Dean Research and Development at Murray Lakshmi Reddy Institute of Technology and Management, Hyderabad. He is finished his MSc in 1988, PhD in 1994 at Department of Physics, Usman University, Hyderabad. He is worked as a CSR Research Associate, Postdoc Fellow, Research Fellow, National Superconductor Fellow, and obtained a DST Young Scientist Project, and it is executed at Department of Physics, Usman University. After that, he is moved to Taiwan and worked as a postdoc, research associate, research professor at Department of Physics, National Taiwan University, and Academic Sinica in Taiwan around 20 years. He has executed several research projects in India and abroad. He come back to India and joined as a professor in physics MLRIT in August 2016. He is expert in various research fields such as ceramic materials, synthesis of nanomaterials, superconductor, ferroelectric materials, and magnetic fluids. He has published more than 70 articles in high impact journals such as PRB, PRE, scientific reports, chemistry, organic chemistry, Journal of Applied Physics, and ACS Applied Material Interface. He's written three books and three book chapters. H-index is 14. All the participants, please join me in welcoming to Dr. G. Narsingh Rao Garu. Thank you. Anna.
Okay. So I'm audible?
Yes.
Is it audible?
Yes, sir. Yes, sir.
Okay.
Yeah, it's audible.
Okay.
Yeah, audible.
Okay. So I will share my. Okay. So thank you, Bhaskar. So what Purushottam told us. So my PPT also already there. So he finished my PPT. Okay. Anyhow, I will just explain what are the things required for material scientists, as well as what important things like Purushottam is doing, that purity of the chemicals. So while watching my PPT, so maybe the importance of the purity is more means it's a required knowledge of purity is essential for some of the properties. Okay, so I'm just Dr. Narsingh Rao, professor in physics, Murray, and Dean Research and Development, Murray Lakshmi Reddy Institute of Technology and Management. I joined here in 2016. So earlier I was in National Taiwan University from 2000 to 2016. Okay, so these most of the work from I did in National Taiwan University only. So now I am doing some dielectric properties like that. So I have established one advanced material lab for dielectric property. So is it audible? Okay.
Yes, sir. Yes, sir.
Okay. Okay.
Sir.
So now my talk will be like this. So I will keep this one. So what we can learn from here, okay? So the importance of materials tetrahedron in a broad way. So these are mostly for what Purushottam told. So that things will be there, okay? So what are the common types of materials? So we all know, we are all teachers as well as students. From long back, we are learning all the types of materials like band gap and magnetic moment, different type of materials. But that conventional type of materials, nowadays there is a particular desired materials, they have some particular names. Okay, so that will also, it will be in my topic. So that is an important role of polymorphs. So this polymorphs is a very important role in is a key role in novel materials. To design the particular material, you need the particular structure. So that's the important criteria to make advanced or novel material. Okay, and determine the properties of materials with band and spin. So we all know this band and spin, that's traditional definition. But later on, there is a modifications of classification of materials in terms of band gap as well as spin structure. So later on, it will be summary. Okay, so that's a material tetrahedron is a combination of four four methods. Like if we can see the picture, so there is a performance. If you want to performance, you have to make a processing, isolate, you have to study the properties and structure also. So these four are interlinked ones. So if you want one particular property, you have to make one particular structure, and it shows some particular performance. So these all are interrelated ones. Okay. So then each of these aspects is dependent on the other. So if you want to make a processing, so you need a better performance as well as better structure as well as better properties. So these are the material tetrahedron. So I just want to show this material scientist how important it is. Okay. So now I will go to the general, means it's traditional. What I mean is traditional classification of materials. So we all will easily tell the engineering students, hey, there is three types of materials are there. So what are they? Like that, we will ask questions for students. Okay. So usually it will be, we are studying since our childhood also, means around 6th to 7th. That time itself, there is a different type of materials are there, like that we are already known. So there is a metals. Metal means we all know that valence band and conduction band will be overlapped. So the electrons will be in between, there will be overlapped. It will jump from valence band to conduction or conduction to valence band. So this, there will be no gap. We call it as a metallic material. Similarly, there is a gap between valence band and conduction band. The band, we call it as a band gap. That means the center point is a band gap or Fermi energy. Whatever we talk, these are the energy gaps. Depends on the energy gap, we will classify the material in terms of different types. So this semiconductor material means it's only small gap. That is compared to conduction band, the gap will be more. Metallic materials, semiconductor will be more gap. So if you go to the insulator, the gap will be higher. So this gap also, there is depends on the material, depends on your availability, depends on your properties. This gap also changing. Initially it will be, they said it will be 0.126 electron volts. So nowadays they said it's only 0.3 or 0.2 electron volts. So above that it will be insulator, like that. So these are the general classification of materials based on energy gap. Similarly, there is a classification in terms of spin alignment or magnetic moment value. So depends on this magnetic moment value. So we classified materials into 5 subgroups. So these 5 subgroups are the ferromagnetic materials. So we all know that ferromagnetic material means the spins are aligned in a particular direction without any external field. So that is a ferromagnetic material. So in ferrimagnet, it's some of the there will be less compared to ferromagnetic. The spin moment or the magnetization is less compared to ferromagnet. So this is a ferrimagnetic material. Another one is antiferromagnetic. Antiferromagnetic means, so it's a magnetization is a spin alignment. There's one particular spin and adjacent spin will be in opposite direction. So there will be net magnetic moment will be 0. So that type of materials we call it as a antiferromagnetic. Similarly, paramagnetic. It is without any magnetic field, it will be randomly arranged. So because of this random arrangement, so there will be no net magnetic moment at paramagnet at 0 field. If you are increasing the magnetic field, the spins will be aligned in a particular direction. So such materials we call it as a paramagnetic material. So another material that is totally different than this all the 4 magnetic materials, that is a diamagnet. Actually, there will be no magnetic moment, no spin moment in a at a 0 field. Okay. So if there is no spin moment at a 0 field, if you are applying the magnetic field, the spins will be aligned in opposite direction. So if the direction of magnetic field is right side, then spins will be aligned in a left side. So that means the net magnetic moment will be negative. So that's diamagnetic behavior. Okay. So this I took from some other website. So okay. So usually the materials means we have to aggregate the atoms. So aggregating atoms means if you aggregate, so in a particular way. So in a particular way, it will be, the properties will be changed drastically. Okay. So if you aggregate the atoms, you can do many things. Okay. In fact, the same atom will give you very different thing if aggregated differently. Okay. Example, the carbon atoms. We can see the carbon atom. So if you aligned in a particular direction with a high pressure, high temperature, you will get the diamond. Okay. Similarly, nanoparticles or carbon nanotubes, like that. So these different arrangement of atoms lead to different properties will emerge. Okay. So that means if it is more different, it will be more different properties you will get. So this is just for different alignment. That means different structures. You will get the different properties or different quality of the material. Okay. So, but in how if we know that everyone, almost everyone, we know that means there will be conducting, electricity is conducting through metals. Okay. So there will be non-conducting is like a wood or some plastic, like that. So there will be, we know that it's almost more than 2 decades, 2 centuries. So there will be, we understand that there is a electricity flows only in some material, it won't flow in other material. Okay. Whereas in other like silk or wool, it won't, electricity won't flow. Okay. Whereas some of the materials, vegetables also, it will flow the electricity, like some like what we call it as the potatoes, and if you keep 2 leads, then you will get the bulb will light. So that there is electricity from vegetables also. Okay. So there is a insulator as well as metals. So we can find out from this type of studies. But in 20th century, once the quantum physics provided scientists with a new tool to probe the properties of electrons. So that means if the same material, you can get the some property like insulator, some property like metal. So this type of material fuel the discovery and understanding of exotic quantum states of matter. So because of these type of new materials, so there will be lot of research is going on because of this different type of properties. Because the same material, you will see the 2 properties, like one is insulator and another one is metal or conductor. Okay, like that. So these are the basic things. So there is a discovery of new materials. I think this one is disturbing. Okay. So there is a discovery of new materials with novel properties is one of the most fascinating aspects of physics. So this is the new materials is fascinating. So that fascinating properties are like spintronics. We all know that we are using latest gadgets. So these all are depends on this spintronic property. That spintronic property is nothing but semiconductor as well as magnetic. So there is a different type of properties. Same material, it will be act as a conducting or semiconducting or magnetic or non-magnetic, like that. So these are the new area, that is spintronics material. So there is a very recent example, that is around 2007. So there is a topological insulator. It's another interesting material. But in mine around in my lab also earlier in 1990s, we used to prepare this chalcogenide material, semiconductor. But that time we don't have much experimental effort, as well as we don't have such type of quality material like what Purushottam is told, it's 7 nines or 5 nines. So that time we don't have that type of material, but that's why we won't get any but special properties of that in our lab itself, we make the bismuth 2, selenium 3 like that. So this chalcozanide materials, we earlier itself we make it, but we didn't study properly. So now it's a 2007, this topological insulator came. So that's because of this topological insulator. Topological insulator means it's like an insulator only in a bulk side. That means in the center it will be insulator. In surface or in sides it will be conductor. So this beauty of this material is a topological insulator. We call it as a topological insulator. That insulator is an electrically insulator in the bulk, that is in the center point, and these metals have surface state as the conducting electron. So these conducting electrons also, compared to conductors, it's a more good conductor. So that's why these materials, they call it as a topological insulator. Okay. So this character offer a low power option for designing a transistor in a fast switching environment. So most of this semiconductor industry, they are using this topological insulators. Okay. So nowadays these topological insulators are very the research area is very boom. Okay. So this recent material, that is 2007. Okay. So a relative newcomer in the field and growing importance to condensed matter physics in the topological insulator. It manipulates the electricity unlike anything else known in nature. So in nature, you will get only one particular property. If one is conducting, another one is insulating. So there will be no material. It will show you both the properties at a time. Okay. So this type of newcomer, that is a topological insulator, is very good for industry, semiconductor industry. Okay. In its interior is a bulk. The topological insulator stops current just like on a normal insulator, but at the edges, in the case of 2D material. So if the 2D material means there will be only two directions, it will be there. The third direction will be almost negligible. So that type of like a plate, like a thin film, like that we call it as a 2D material. So in the 2D material, the edges are conductors. The edge is a conductor. Inside it will be insulator. Whereas in the 3D material means it's a bulk one. So in the 3-dimensional, you can see that one. So in the 3D material, you can it will be the surface is act as a conductor. Remaining interior is act as a insulator. So this is the property of the topological insulator. So this behavior arises from the atomic structure of the material itself. So the small imperfections or changes in the surface won't disrupt or reroute the current. So this important thing is in atomic structure level. So we are getting this type of behavior. If the material is very pure, so you will see this type of structure. So that means in surface it will be conductor and inside it will be insulator. So this type of behavior you can see here. So this is a bismuth tellurate, is a well-known topological insulator. So they make they already, it's a known material only, but this type of property they saw in 2007. Okay. So in Princeton University, it's there is our actually earlier our collaborator Hussein. So Hassan. So is this they make this type of angle resolved photoemission spectroscopy. So this word we never listen this type of words in earlier. Okay. So this angle resolved photoemission spectrum. So it will give you the band structure, or it will give you the energy bands, how it will be. So you can see that the down one, this one is a valence band. This is a valence band. This is a conduction band actually. This one. Okay. These two arrows is a conduction band one, but this you can see it will be touching this. This is the Fermi level. So less than the Fermi level, it is coming down. So in the surface only, it's only in the surface, not in a center point. Okay. So this is angle resolved photoemission spectroscopy. Once this instrument is showing this type of things, then they are just putting all the material. So like our COVID, so we are putting the people, everyone is you have to test. Similarly, they tested lot of materials, but only few materials they showed this type of behavior. Okay, so that means the above the bulk valence bond, that is this one is a valence band above one. So this this energy level, so it is coming towards the valence band side. Okay, so this white line is combining at a particular point, that is they say there is a Dirac cone. That means there is a wave numbers and banding energy. If you calculate that one, it will come like a cone. So that particular cone, it is touching that one. So this is due to this one, they said it's a conducting material in a surface. So inside it will be insulator. So this is the beauty of angle resolved photoemission spectroscopy. So they make bismuth telluride. Okay. So this bismuth telluride, it shows the topological properties. Okay. So this there also different type of things are there. So there will be another topic, that is polymorphism. In bismuth telluride, there is a different type of morphologies or different type of structures are there. So depends on that structures, it will show that topological insulator. Okay. So there is a polymorphous for the novel materials. It's a very, very important one. So like crystal polymorphous are defined as the that are chemically identical. So the chemical like carbon is there C. So it will be diamond, it may be diamond, or it may be graphene, or it may be like C60, like buckle ball, like that type of things are there. The same material. If you see that only carbon is there, but there will be different type of forms or different type of structure. Okay. So that's a important one in a crystal polymorphism. So this one we will study later, this one. Okay. So there is a polymorphism in drugs also. So due to this drugs polymorphism, so they will it will affect the physicochemical properties. Okay. Such as the dissipation, dissolution rate, solubility, bioavailability, and manufacturability. So these are the affected ones due to this polymorphism of that particular drug. Okay. So similarly, there is a in nature wonder is there. There is a genetic polymorphism. So we know that Fight Master Ram Lakshman almost it will be similar. Okay. So most of these twins, so we cannot identify through DNA also, I think. So they will identify only the palm line. Okay. So that's genetic polymorphism. Okay. Now I'm going to explain about the crystal polymorphism. Okay. So in material science, the polymorphism is the ability of solid material. So it will act as more than one form of crystal structure. Okay. So the polymorphism can potentially be found in any crystalline material, like in polymers or minerals and metals. Okay. So this polymorphism in crystallography, the condition in which solid chemical compound exists in more than one crystalline form. So these forms differ somewhat in physical and sometimes chemical properties, but there is a solution and vapors are identical, like carbon, diamond, graphene, and if buckyball, if you melt that one, you will get only carbon. Okay. So that type of polymorphism will be there in a crystalline form. So this polymorphism is not a new one. It's a very old theory, that is old. They found in 1820, almost 2 centuries ago. Okay. So that German chemist, he found that different crystalline forms of a same material. Okay. So this is the polymorphism in crystalline polymorphism. So now I will take one type of means the material polymorphisms, different type of material polymorphisms, like it will give some specific chemical composition to crystallize in more than one form. So this generally occur as a response to change in temperature or pressure. So if you change the temperature also, you can get the different type of material, or you can change the pressure also, you'll get the different type of material or structure. Okay, so the different structure of the such chemical substance are called polymorphic forms or polymorphs. For example, the element carbon. So carbon in nature in two different polymorphic forms depending on the external pressure and temperature condition. So one is a graphite with hexagonal structure, another one is a diamond with isometric structure. Isometric structure means similar structure. Okay, so that's a graphite and diamond. So nowadays another some more also came, like buckyball and carbon nanotubes. Okay, so these are the different type of, once again, polymorphism of carbon. Sorry. So the composition of SiO2 is a general one. That's Isuka, we call it as a, okay, SiO2 is found in a large number of polymorphs. Among them is quartz is one example. Okay, so there is a different type of silicon oxides will be there. So there will be, depends on the temperature, how we make that one different temperatures as well as different pressures. So you will get the different type of silicon dioxide. Okay, so this is a polymorphism of different materials. So now I will take a particular material what we studied in detailed. Okay, so that is layer transition metal dichalcogenide. So this dichalcogenide in earlier also we make in our laboratory. Okay, so just that similar type of metal dichalcogenide. Here its important thing is the purity of the material. If the purity of the molybdenum, tantalum or tungsten as well as sulfur, selenium, tellurium. So these tellurium. So these materials quality or this materials purity is most important. So most of these studies, or it will show different properties depends on that particular quality of the material. Okay, so have attracted renewed interest owing to their rich physical properties and promising potential applications. For example, artificial van der Waals. Actually, this layer transition metal dichalcogenide. So if you, there is a few layers will be there, we can remove that layer also without any chemical or thing. Just stick that tape and just pick up, you will get the one layer of this layer transition dichalcogenide. Okay, that's because of this van der Waals heterostructure. So it won't attract each other. Depends on that's a I on-off current ratio. So it will be removable. So that's why we call it as a artificial van der Waals heterostructure. Okay, so this is the beauty of transition metal dichalcogenide. Okay, so topological field effect transitions based on quantum spin Hall effect. So these are the properties we can get the quantum spin Hall effect. So these are the mostly useful in semiconductor sensors. Okay, the quantum spin Hall effect. These are the novel property as well as there will be devices like semiconductor sensors. Okay, at the same time there is a charge density waves as well as superconductivity also observed in transition metal dichalcogenide. So it may be molybdenum or it may be tungsten. Some will show that superconductivity. The molybdenum tungsten will show the superconductivity. Molybdenum also shows superconductivity, but it's very, very low temperature. But it shows remaining properties like topological insulator type and it's a quantum spin effect or Dion's oscillations. There is a different type of terminology came. Okay, what I told earlier, it is a general terminology. We know only conductor, semiconductor, insulator. In that semiconductor itself, there is a different type of properties. That properties will classify the material. Okay, that's a different type of thing is happening nowadays. Okay. So this two-dimensional molybdenum telluride exhibits an different type of polymorphic nature. Okay, so it will show the stable semiconducting hexagonal structure, that is a 2H structure. 2 means it's in a unit cell there will be two atoms will be there, so that's why they make it as a 2H. That is a stable semiconducting hexagonal structure. Okay, that is a molybdenum telluride. And another phase is a metallic 1T prime. This is a tetragonal. So this triclinic. So this triclinic phase isolates these two phases is appears at same room temperature. That's at room temperature it exists both phases. Okay, depends on your preparation method or preparation condition. Okay, but this 1TD there is a phase transition from 1T prime to 1TD at around 245. At 245 K, so there is a possibility of phase change material, phase change. So that's why this polymorphism presents a new opportunity in developing a phase change memory, high performance transistors, and spintronic devices. However, it also poses challenges in synthesizing homogeneous, that means in a single phase, precisely controlled, is a very, very difficult. Is it audible? Is it audible?
Audible.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. So this is the challenges we faced in synthesizing this homogeneous MOTE2, okay, with the different structure. So you can see that there is a 2H material. Okay, 2H material is showing is 2H phase, that is hexagonal phase. Molybdenum and tellurium atoms are arranged in a plane hexagonal symmetry, and out of plane this is in plane. Okay, this we can see then a screen is along the C axis. So this hexagonal is along the C axis. You can see the hexagonal. Okay, whereas in other out of plane, so you can see the trigonal prismatic coordinator. So there is a space group. So earlier Dr. Jagadish Babu, so he told a lot of things on X-ray type of things. So here, so his help may be more accurate here because the structures are very, very precise. So if you are making one material, so you cannot make all the properties yourself. So you need some collaboration. Okay, without collaboration, such type of properties you won't get. Okay, because if you have a more sophisticated instrument, but you cannot get the proper material, it's a useless. Okay, so maybe somebody is playing with me. One minute.
Hello.
Good.
Hello.
Okay. Now I will disable the participant. Okay. Okay. So this is 2H material, hexagonal material. Okay. So in out of plane it will be trigonal prismatic, and in plane it will be hexagonal. In plane means along the C axis. That is the condition. So here it is 1T prime phase. They are arranged in a plane monoclonic structure, and out of plane octahedral coordination. Here is a 8 atoms will be there, octahedral, with a space group of P121/M1. So there is a different type of space groups are there. It is same material, if same monoclonic structure, but there is a different type of space groups are there. But this one, there is another ocean, so we can study that's a different subject actually, the crystal diffraction. So I remember in my MSc time, we have one book that is a Kuliti, X-ray diffraction by Kuliti. So that is the Bible of X-ray fellow, X-ray diffraction, whoever studies diffraction. So That's the Kuliti book is the Bible for X-ray diffraction. Okay. So this both 2H and 1T prime, that is hexagonal and monoclinic phases, not only are stable at room temperature, it will go up to 900 degrees centigrade without changing the phases. Okay. But at low temperature, it some 1T prime, it will change to 1D. Okay. So this is the and stability as well as different type of properties. It will show this MOTE2, that is molybdenum ditelluride. So the preparation of this material is very difficult one. Okay, and you need more patience to watch this one. So it may take 2-3 weeks to make a very good single crystal. Okay, very good single crystal. If you make, then it will be your thesis will be over. Okay, but that should not be there in a literature. That's another important point. Okay, for growing large single crystal, the purity single crystals of controlled structure types by using novel chemical vapor transport method that involves a mixture of molybdenum and tellurium bromide. So this tellurium bromide, they use it will the tellurium bromide converted into TeBr2. Br2 will be acting like a there's a vapor transport material, the Br2. Okay, so the tellurium will act like both will be combined together and it will form as a molybdenum telluride. So MOTE2. So Br2 will be this transport agent. Okay. So by controlling the temperature profiles, these are the profiles of the temperatures. What Purushottam told in microwave, just press the button, so it's automatically temperature will set. But here we have to set the 3 different zones: the first zone, second zone, and third zone. So this second to third zone is very important one. Okay. So first zone is from here to, there is a source material. You can heat up to 1050, then slowly decreasing the temperature. So you can get that single crystals with using this second to third. This is the growth zone. So at lower temperature, you will get another type of crystal. Okay. But so we don't know exactly, initially we don't know exactly what is the 2H material, what is the 1T prime material. So you can, I will show you the picture, so you can identify this 1T or 2H, it will be good. Okay. So these are the different type of structures we can make with just changing the temperature. Here only the temperature is changes, nothing else. Okay. All are same molybdenum, same TeBr4, so same crucible. This is a double-walled quartz tube. Same thing. Temperatures, except temperatures, everything will be similar, but you will get the 2 different type of materials. You can see that 2 different type of materials. Can you identify which one is a 2H, which one is a 1T prime? So this making 1 centimeter, it will be more than, I think, it will be $300 or $400 US dollars. Okay, that single crystal. So this type of single crystals, getting this type of single crystals, so Purushottam help is required because he has a very nice material, means a 9 purity, that is the 9 nines. Okay, so this type of material, for this time we will pure ourselves the material. So we just solder inside the quartz tube and just we melt that material and we collect that end material. So there will be possibility of purify that material, the tellurium, especially tellurium. Okay, so these 2 are different types. But if once we saw this material in the same temperature, then we cannot recognize which one is which. Okay, so that's initially we face a lot of problem. So later on we systematically studied and we missed the temperature profiles we set, and we got 2 beautifully crystals with different properties. Okay, so this is the 2H material. Okay, so almost similar. If you just keep one tape, it will get the layer. One layer you will get one atomic layer. Okay, so it's not easy to make a thin film of one atomic layer, but here you can scratch with a scratch tape. You will get the atomic level crystal. Okay, so similarly this one also. These two are, if looking, it will be similar. Okay, not only looking, you can see the crystal structure also. Okay, just X-ray. So these are the methods we used for properties purpose, that is synchrotron radiation. Last lecture that Raghavendra Reddy is mentioning about synchrotron X-ray diffraction. Okay, so in Taiwan there is a synchrotron powder diffraction is there. So we have a collaboration every year, 3-4 times we will get the time. So at that time we will pick up all the samples and we will measure that type of measurements, X-ray measurements. Okay, so that is a X-ray purpose, and there is a inbuilt in-house X-ray diffraction also there. Okay, so there is a magnetic measurement. We have at that time we have a sample vibrating magnetometer. Okay, quantum design. You can go up to 1.8 to 350K or 700K also we can go. So there is a isothermal magnetization up to 9 Tesla we can measure. Okay, so there is a heat capacity measurement, that is a physical property measurement system. So we can get very good thermal property like resistivity as well as heat capacity. Okay, so using these methods we incorporated these things. Okay, you can see now the X-ray diffraction pattern of 2H and 1T prime. So how we can recognize both are similar? Is it not? So both the structures are same, except this 0010 intensity is very little bit higher. Here it is not there, but remaining things identical. Okay, so this is a single crystal. If you saw the single crystal, then you can mix together. They both are same. So then you just grind it. Then you can make a powder diffraction. So initially maybe we did like that also. We don't know exactly that. So in later on, once in a papers came, then we also thought, hey, we already measured, make the sample, but we didn't get that type of property. Then we gone through in a detail, then we will get the different type of thing. Okay, you can see the powder diffraction. Same crystal, this crystal we grind it. Okay, this 2H isolate 1T prime. So we grind these crystals, then we will get the powder diffraction. This also in a synchrotron X-ray diffraction. Okay, so you can see here the clear. Is it not? So you can see the peak positions will be different and total number of peaks also different. Okay, so this one is hexagonal structure. This is a monoclinic structure. It's a more less ordered structure. This one is more ordered structure, we can say. Okay, so this is a 1T prime. This one is 2H material. So if we make that fittings, everything, that's the extra effort. Okay, so that's what Jagdish Babu told. There is a different packages are there. So once you got some peaks, then you can fit in that percentage. But before that, you have to make the crystal and you have to make the separation of two different types. That's a headache thing, as well as there's another very means if you check that one, go on checking. So if you find this one, oh, I got this hexagonal structure, I got this monoclinic structure, then your feeling will be different. Okay, so that what I am want to tell is, so everyone should at least 2 years without any worries, just to research. So if all people may not be possible, but my suggestion is make that type of things. Now that Raghavendra Reddy or Purushottam, so they are 24 hours research only. They don't have other topics. We have to teach, we have to attendance, we have to marks. These things are there to reduce our research thinking. Okay, so but that type of habit, it requires for this type of works. Okay, required this type of works. So this is refined room temperature synchrotron X-ray diffraction pattern. Okay. So whereas in a single crystal, it will be both are similar, but in powder diffraction, it's totally different. Okay. So then we thought it will be two different materials. Okay. Then, so in normal, so we will just keep it in a means like resistivity purpose, like magnetic, like any other properties. Once this X-ray, this identification is over, then remaining things automatically it will be finished. Okay. So you can see there is a structural. This is a crystal maker. There is a one package is there. So if you import that CAF file of this MOTU to already, so in the long back our forefathers already made this type of compound earlier itself, but they didn't study this type of property. Okay, so then we took that type of this one also we are comparing with old data, so then we can get that crystal maker, so we can draw the nice pictures to make the publisher will be happy. Okay, so this is the crystal maker pictures of 2H. Okay, so that is hexagonal structure. So this is 1T prime. This is a monoclinic structure. This is the TD. This is also monoclinic, but the space group will be different. Okay, so this TD is means there is a 1T prime to PD. There is a phase transformation with temperature, decreasing the temperature. Okay, so there is a phase transformation. Here it is two different materials we can make at a particular room temperature itself. These are stable. So these are not stable at room temperature. One is room temperature, one is low temperature. Okay, so depends on the material, processing conditions, we will make these two, and depends on the measuring conditions, we will get these two. Okay, so that's two different polymorphism. Okay, you can see now clearly. So there is a resistivity of molybdenum telluride in a hexagonal. Okay, so this is a semiconducting behavior or insulating semiconducting behavior. Okay, so if we make already we are instrument, so we make 0 Tesla and 9 Tesla also. Is there any changes are occur or not, like that? So nowadays this type of studies are more, because at low temperature, at a higher field, there is a oscillations will come. Okay, so there is a something, there is a terminology is there. So there is a oscillations will come at high field at low temperature. Okay, for that purpose, we will check every time whenever we keep in a PPMS sample. So we will do all types of things. Okay, so that's another thing, available thing. But okay, so this is a 2H material. This one is a 1T prime. You can see here. So up to this point, so there is this only small range around 250 or 240 or 260. This is this range. Okay, so there is a structurally change. This one is a structure change. So here it is a semiconducting behavior. It's a 1T prime. Okay, so this structure is 1D. Okay, so TD and T prime. So these are the two different material structures. One is a T prime, another one is TD. Okay, so if you measure the low temperature X-ray, you will find that type of structure. Okay, so this is phase transition with decreasing temperature. This is due to the conditions, making conditions. These two phases will come. Okay, so that is 2H material and 1T prime material. So these are the properties automatically we can measure. Okay, so simultaneously you will get IV curve. Okay, with different magnetic fields. Okay, so these are the this mobility also we can calculate. Okay, with different orientation we will measure, because it's a single crystal. We will measure X, Y, and YZ direction. So then you will get the mobility. Okay, so this mobility of 2H, you can see around low temperature, that is around 400. Okay, so this is 2H material. Okay, so this all resistivity we can make. So only up to 50 only we can make, because below that one it's a very high resistivity. So that's why we cannot make that property. So here it is 1t prime. You can see there is a magnetic field, and without field also there is a no change. Okay. So, but only the cooling and heating it is changing. So that is the first order phase transition, that is from 1 t prime to td. Okay, first order. If there is no order, there is no hysteresis, it will be second order. So that's a important point. So this is a first order transition. Okay. So if you make IV curve, then here it is, you will get the mobility parameter. That mobility is compared to that one is almost 4 times less. Okay. So this is the 1t prime material. Okay. So same thing. What I told is, if your material is there, you just kept in all the instruments, you will get the data, then just analyze. So this is a phase transition in a susceptibility magnetic, but there is no magnetic element. You can see here, molybdenum is not a metal, is not exactly magnetic. Okay, tellurium also not magnetic, but at structural change, but the value also very small, 10 to the power minus 8. Okay, so at a very you can see distinguish the phase transition is there. Okay, so that means it's a phase transition is around 260 or 254, like that. Okay, so similarly the heat capacity also shows some kink. So this heat capacity will recognize the phase transitions very clear. Very small phase transition also we can identify through heat capacity data. Okay, so you remember this point. So then later I will tell it's not possible. Okay, because here the phase transitions clearly we can observe through heat capacity. So this is the material of 1t prime. Okay, so in a hexagonal one is only semiconductor or insulating type. This one is a metallic one. Okay, so in similarly Raman spectra also, that for both samples there is a different type of means polarization peaks will come. Okay, so it's a 2h as well as 1t prime. So it depends on the thickness of the layers. Okay, it's a 10 layer, 50 layer, and bulk. Similarly 10, 50, and bulk. So if you are reducing the layers, so you will get some extra peaks also. That's another trend. So actually I want to keep that video, but it's okay. So this is a theoretical background. From theoretical background, you can see there is a means in a 1t prime. So there is a means valence band and conduction band is almost close. Okay, this is band structure calculation. For this purpose, we have to ask some our theoreticians to help us using this type of studies. One, we cannot study all these, so that's why we have to give some to some others. So this is the scanning tunneling microscope. So it's very expensive one. So it's very hard to get the time. But this importance of that material, we got this type of spectra. Okay, so you can see this is A and B is 2H material. So there is a 1T prime material. This is a 2D. Okay, you can see here there is a clear change of this. Okay, the structure is changes. Okay, so for that purpose they make IV curves. So how it will be changes. Okay, so this one is the F and G is the TD prime, TD. So this one is a low temperature they make. Okay, these two are room temperature one, A and B, and C and D is a room temperature because the structure is 2H and T prime. So this is F and G is a low temperature one, that is a TD structure. Okay, for that purpose, so we make 3. Okay, so this is this work. This total work is published in ACS publication, that is chemistry of materials. Okay, so that impact factor of chemistry of material, it will be around 9.5. Okay, so when we published around 9, so now it will be little increases. Okay, so it's most of the work is sharing by so many authors. You can see that different. You can see almost 10 or 12 authors will be there. So everyone sharing sharing that particular idea. Like this type of spectra, somebody will make theoretical one, somebody like that. So we have to collaborate the people, then you will get the good publication. But in our engineering colleges or some other places, they ask first author. How you will get first author doing all these things? Okay, so it's a first author or second author is no matter. The contribution is important in my opinion. Okay, so this is Shankar is our student. So this one is okay. So this is chemistry of material story. So how much time I left? Hello? Continue, okay. So that is topological for band structure calculation according to band structure, okay. So here it is a spin structure. So these totally two different aspects, okay. So one is topological insulator, that is metallic isolate insulator. Now it is magnetism, that is spin dependent, okay. So usually if you get one maxima, it's like antiferromagnet, we all know that there is a sharp maxima at antiferromagnetism, where there is a sharp increase at ferromagnetism. There is a no change, that is a paramagnetism. We know this bookish definition, okay. So these are the para, ferro and antiferromagnetism. But here, so there is another type of magnetism, that is low dimensional magnetism, okay. Low dimensional means less than 3 dimensional, 1 dimensional or 2 dimensional. 1 dimensional means in only one direction the spins will act. Only one direction the spins will be effective. Another 2 directions there is no effective on that spin. Similarly, 2 dimensional means it's a surface one, as like what we call it as a phase. So that is there is only 2 directions it will be affecting, 1 direction not affected. So that means you can see here there is only single line, it's a 1 dimensional one, okay. There is 2 lines, this is a plate type, okay. Here it is a bulk one, okay. So these 3 will different acting will differently. So here you will get the exact what bookish definitions you will get. If it is antiferromagnetism means antiferromagnetism, ferromagnetism means ferromagnetism. But here, due to there is a frustration between these spins, you will get the different type of magnetic behavior. So that usually call it as a low dimensional magnetism. So it won't show any well-defined antiferromagnetic or well-defined ferromagnetic. But in between, it will show some type of fluctuation, that is a quantum fluctuation, okay. So this, if these quantum fluctuations, it will also helpful for computerization, okay. So if it is data computing, this type of materials are useful, but exactly I don't know where they will use, but this theory or they use or the material they use, I don't know exactly. I will maybe next time I will check, okay. So this is the spin dimensional, depends on the spin. So there is a dimensionality depends, 1 dimensional, 2 dimensional and 3 dimensional, okay. So when the spin interactions are large along the 2 directions of the space and weak along the third one, the spin system can be viewed as a stacking of quasi isolated magnetic layers. This is on first one is magnetic chain, okay. So only one direction the magnetic spin will be there, another 2 direction there is a no spin. So this is the magnetic spin direction, 1 dimensional and 2 dimensional. 3 dimensional means it's a bulk, like exact antiferromagnetism or exact ferromagnetism, okay. So then, so there is a frustration magnetized. So that's the same thing, it happens. If there is a spins are aligned like this, one is up, one is down, one is up, one is down, then there is no frustration count, okay. If it is a triangular one, okay, so there is a one is up, one is down, third one, where will it will go? So that type of frustration will tell these low dimensional systems are important. Okay. In here also, one is up, one is down. These two are where it will go. So there is also frustration. So this frustration, they call it as a geometric frustration of spin. So this is another. The terminology will change. The depends on the property. Okay. So this is a geometric frustration spin with a different alignments. For this different alignments, there is a different type of theories will come. Okay. So I'm not going to the theories. So I make one type of crystal, that is Ba2CuTeO6. So this is a double perovskite type, but it's not like that. So we grow this single crystal using the flux method. Okay. So this flux method, we make this single crystal. So it shows some hexagonal structure. Okay. But it's only 1 or 2 mm. It's very difficult to make this type of single crystal, very small one. Okay. Is remaining things is very, very small. So only we will get only few will be higher size, remaining will be smaller. So you can see this unordered structure. Okay. So that means very low ordering this triclinic structure. Okay. So these parameters, so these all are from once again that XRD of synchrotron. So you can see here the single crystal diffraction pattern using an X-ray. So we make here, this direction is along the 00L plane. Okay. So we are making the crystal like this and we are sending the laser. So then the X-ray beam, then it will get this type of structure. So you will get the single diffraction pattern of single crystal. So it will be along 00L plane. Okay. So the growth direction is along the C. So the structure, this the first one, this A is there is a 2 types. This polymorphism here also there. Okay. So this what I am showing is all these all polymorphism materials. Okay. So these 2 polymorphic materials. One is this one is tetragonal structure. Okay. This tetragonal structure A. This B is a triclinic structure. What I am interested on this triclinic structure. Okay. So there is a combination of copper oxide, this CuO6. Okay. Then there is a tellurium as well as there is a tellurium is 2 positions. One is one Te1 and Te2. So depends on this oxygen orbital. So we will get the magnetic moment. We explained that one in terms of 2-leg spin ladder. There is a chain and a plane. There is a 2-leg spin ladder. There is a different type of low dimensional systems are there. Okay. So this is under 2-leg spin ladder system. Okay. It's a Ba2CuTeO6. So you can see this structure. This is we make it on at a high pressure state. Same material. Okay. Same this Ba2CuTeO6 crystals. We make it in a high pressure. Then it will come as a powder. Okay. High pressure one. So that high pressure one is shows this one tetragonal structure. Okay. So this is a tetragonal structure, and as it is prepared one is triclinic, tetragonal and triclinic. Okay. So this is a tetragonal structure. It's a high pressure material. Okay. So this is a triclinic structure. Okay. So this is a ice prepared sample. Okay. There is a well ridge weld fitting. So it will shows all the material is same. That is triclinic. Here it is a tetragonal. Okay. So then you can see if there is a different type of this is at a 6 gigapascal. Okay. I just draw the one more time. There is a small range. So you can see this tetragonal one. Okay. This is a triclinic one. So if you say this is a 300 at room temperature, at low temperature, there is a phase change also in between. So, but that we are studying once again. Okay. So around at below room temperature, there is a once again phase change. Okay. Because you can see there is a 2 peaks. Here it's a 3 peaks. Okay. So the such a type of arrangement of Bragg's peaks. So you will get some different type of structure. Okay. So this is one structure that is tetragonal. This 300K is triclinic. This is gigapascal is tetragonal, and 10K is some other structure. There's a space group only change. Triclinic only, but different space group. Okay. So this is the structural studies of Ba2Cu-TuO6. Okay. Then we have a powder. This one is a powder actually. So this is tetragonal structure after heat treating in 6 gigapascal at 850 degrees centigrade. Okay, so we got like this behavior. So one can identify which type of behavior it is. So normally we will say it's a antiferromagnetic because it's going down. Okay, but it's not antiferromagnetic. If it is antiferromagnet, if you make a differentiation of this one, there should be one maxima or minima. Okay, so here there will be smooth increasing or smooth decreasing. There will be no anomaly in dk by dt. So that means there will be no long range ordering. Long range ordering means 3D. Three-dimensional magnetic ordering is not there in this sample. So then they said it's only low dimensional magnetism. Okay. For that low dimensional magnetism, there is a lot of theoretical calculations are there. You can see this equation. Okay. This is a one-dimensional chain equation. So depends on the x. That is J is the interspin exchange coupling, intra-chain exchange coupling. That is the J value. So this depends on this J value. So there will be magnetism will be changed. So this fitting we will make in origin. So very easily. Okay. So this is origin fitting. So there's an equation for interchain exchange coupling. There is a dimers and trimers. There is a different type of equation. Depends on your spin structure. You can identify this type, which equation is useful for you. Okay. So then that is a 6 gigapascal one. Okay. So this is only one-dimensional one. It's just increasing at low temperature. So this is actually it's a powder. If it is a crystal is there, maybe its story will be maybe different. Okay. So here we have a single crystal of that Ba2Cu-TuO6 triclinic one. Okay. So you can see because if there is a different direction, okay, H is parallel to AB, H is perpendicular to AB. That means along the C-axis and parallel to C-axis. So if you make the surface different way, so the magnetic field will be in a different direction. So you will get the different type of magnetization. You can see here. So actually, if it is normal condition, you can say hey, there may be some experimental error. But we measured this type of sample so many times. Okay, are so different type of different crystals also we measured. You can see here there is a dk by dt. So actually it is a 75. You can see around 75 there will be maxima. Okay. So what I told is earlier, if it is maxima is there, there will be dk by dt will be different. But you can see around 75 there is no change. There will be no change is there. So that means there will be no long range ordering parameter is exist in this compound up to this temperature. Okay. So but at low temperature around 15. Okay. So there is a anomaly is there in dk by dt. Here also there is an anomaly. So once we made this type of anomaly, then we measured at low magnetic field, what will happen? So there is a two different directions the curve is going out at 15K. So at parallel perpendicular to AB, it's going down, and parallel to AB, it's going up. So that means there is a spins are acting in a different way in that crystal. Okay. So this is at 15K, there may be possibility of long range ordering. Okay. So this long range ordering only in one direction, not all directions. Okay. So if it is all directions are there, then you will get the very nice gamma maxima in heat capacity. Okay. So this is different with a different magnetization. You can see the H is perpendicular to C. So it's only going up only, but parallel to C. So if one initially it is going down, suddenly it is flipping. So they call it as a spin flip transition around 15K, 15 kiloair state at magnetic field of 15 kilo airstrate, this sample exhibits a spin flip transition. Okay, so that we can see in a hysteresis curve. You can see here around 2K, so around 15. So you can see there is a change. Okay, so this change we call it as a spin flip transition. But without that one, that's another one, which is parallel to AB, there is no change in dm by dh. But here there is a change in H perpendicular to AB. That means parallel to C. Perpendicular to AB means parallel to C. Okay, and along C, so there is a different spin structure is acting. Okay, so similarly, what I told is heat capacity, it will show exactly where the transition will be. But here the transition is not showing anything, but only small kink is there at 15K. Okay, so this we calculated and we consider so many times. So that means it's only 8% of the total spins only acting. That's why we won't get the complete peak or lambda type peak, because all spins are not acting at that particular temperature. So if that particular temperature all acting, then the maxima will be around 0.48 we are getting. This one is only 8% of spins are aligned at particular. Otherwise, it should show 5.76. The entropy should show 5.76. Okay, but the entropy, the delta S, we are getting only at 15K, only 0.48. So that means only the percentage, 8% only spins are acting in that transition. Okay, so that then we asked our theoretician to make what is this condition. So then they made a lot of calculations. Okay, here and there, and so many different approaches, different thinkings. Then finally we will get the different type of spins. So there is this arrows all are spins. Okay, we came from that copper one. Okay, these all are copper. In between there is a tellurium and oxygen will be there in surrounding, like that. But here the beauty is there is a 3 major contribution, that is J1, J4, J5. So we have so many J7 spins. There is a this how we can calculate the what is the J1, J4, J3, J4. This one is depends on the distance between these two. If the distance between these two is small, then the interaction strength will be more. Okay, so this depends on the distance, the interaction strength will be depend. So there will be actually J1, J2 almost similar distance, but J2 is, they calculated this, J2 is not exactly what we are getting as a combination of these. So then only J1, J4 and J5 is acting, more energy is there. So that means these interactions are strong. So from these 3 interactions, we will plot one more diagram. Then we will see this type of diagram, J1, J4, J5. Okay, so this J5, J4 in between J4, J1. So this is like a ladder. Okay, 2-leg spin ladder. We draw this one. Then we publish that paper in PRB. You can see this paper. So it's almost my 3 years effort. Means in between I will do some other things, but I concentrated mostly on this material almost 3 years. Okay, 12 to 16, that is around 15 it will finish. Okay, because of that particular, at 15K only it's created lot of problem, but that 15K only it published in PRB. Otherwise it will publish in JMMM or some other journal. So whenever we saw something, then that one is a more interesting one. So I saw in one of our professor in BRC, actually is I think well-known EPR expert. So usually we thought if any peak is coming, so we are happy. Hey, some peak is coming. But he is watching where is the bump is coming. So that's a different approach. Depends on your experience, you will get that type of things. So that's why I'm saying people just make your total life 2 or 3 years, dedicate to research, then you will get means that taste will come. Okay, so that's this one. So still time is there, or I can stop.
Yeah.
Just
Yeah,
only
you
just
conclude.
rough, just similar type. Okay, so this is another type of polymorphism, PBTASE2. Okay, so here also we make a single crystal. Okay, so this is a single crystal. So this is non-centrosymmetric material. One is there is a two phases are there. One is centrosymmetric, another one is non-centrosymmetric. Centrosymmetric is no use actually. If non-centrosymmetric is there, there is a lot of extra things will be we can make. You can see these two structures, P6 divided by MMM and P6 bar M2. So these both are same peaks, okay, except the small change in intensity. Okay, so at earlier stage itself, they make like this structures means what? It's a wonder. Okay, so that means it's very small difference. It will act as a different way. These are our sample. These data points are our sample. These are the literature PCPDF file. Okay, so you can see there we have one peak. So that means it's a this type of structure. Okay, so that is P6 bar M2. So this is non-centrosymmetric. So then we play that one. We make some magnetic measurement. You will get the magnet and it's a superconducting. Okay, so the superconducting behavior, we got that one. So then we make superconducting properties with the different fields, how we can get the HC2 critical temperature. So this actually I left in 1995 in India. Then I make it in 2015, this type of graph. So almost 95 to 15, almost 20 years. So I never worked on superconductivity in Taiwan. So while coming, so I make another small contribution on superconductivity. Okay, so this is PBTA SC2. Okay, so there is some of my publications related to single crystal. Okay, so this PBTA SC2 I explained, and MOTE2 I explained detailed. BA2 CU TEO6 also I explained. There is another Ni2 NB BO6, and there is a CAFE2O4. These are the single crystal works, and some more also there. So for the time, this one, then I will make it complete here. Okay, so my summary, the goal of material science and engineering to design the material with a certain set of properties, so which gives a certain desired performance using suitable processing technique. So the material can be synthesized and processed. The processing also determines the structure of the material. So the material new classification based on, earlier we have a generalized classification. So there is a new classification based on band structure, that is Weyl semi-metals. Weyl semi-metals means there is in a surface that valence band and conduction band is coincide in a same point. Okay, that is a Weyl semi-metal. It's a nice, it's nothing but a topological insulator only, but they are making in a same point. Similarly, superconductors, topological insulators. So these are in a band structure. Another one is a spin structure. So there is a one-dimensional, quasi-one-dimensional, two-dimensional, and three-dimensional magnetic material. So how the processing and structure depends on the material properties and their performance. So these are my things what we did in the last 20 years. Okay, so these are so now I am establishing one advanced material laboratory in our institute. So we have a DST project around 50 lakhs. So that's the SERB one. So we purchased one instrument, that is Nova Control impedance analyzer. So we can measure 3 microhertz to 300 kilohertz. So large band width we can measure. So at room temperature and above at a time. Okay. So thank you for your listening. So usually in Albert Einstein told, so I do not teach anyone, I only provide the environment in which they can learn. So what I am saying is, if you make your time to concentrate on research side, whatever the field, so that concentration is important. So you will get the what you are get some satisfaction on that. Okay. Thank you for your organizers to make me to give this type of webinar. Okay. Thank you very much.
Sir.
Thank you.
Thank you very much, sir. We have few questions in the chat box, sir.
Okay, no problem.
Sir, the question is from Sri Venkatakrishna, sir. What is the use topological insulator in industrial as well as normal life?
Yeah, the topological insulator industrial is, I am saying, that the semiconductor industry, they are using like a sensor and MOSFET. These all are the nowadays they are using this topological insulating materials only. In normal, we don't need that type of things, na. So we required in normally we required semiconductors and insulators.
Yes, sir.
Yeah.
So next question from Uma Maheshwara Singhar. What are the application of these materials? What is the present research work going on?
Which one? One more.
What are the applications of these materials?
These materials, I told no, this one. So there's a superconducting properties are there. That superconductor is very small, low temperature, but there is a for theoretician purpose that material is enough. Okay, but this MOTE2 and this material is nowadays is very popular material. Okay, it's a topological insulator, and there is a Wiley semi-metal. So where this superconductor I told that is a PBTESC2. Okay, so this is a Wiley semiconductor. MOTE2 is a means like a topological insulator. Okay, so here also there is a lot of applications are there. Yes. So here MOTE2 we will use that semiconductor industry, advanced switching purpose.
And next question is from C. Venkatakrishna. What are the applications of 1D and 2D prime polymorphism in different fields?
1D, 2D, yeah, there is a lot of differences. Na? You just take it as a carbon. Okay, if carbon in 1D, so you will get the very huge mechanical strength. Okay, so this one also, there's a 1D, 2D, there is a lot of applications. Strength as well as in magnetism also, there is a 1D, 2D also, there is a lot of applications are there.
Sir, how many type of crystal structures are there? Is O2 stay in solid crystal?
What?
There are two questions I have added, sir.
Okay.
How many types of crystal structures? That is one.
7, na? We all know.
Yes, sir.
7 crystal structures.
Is O2 stay in solid crystal?
O2.
O2.
Yeah, almost. Oxides are O2 only, na?
Yes, sir. Question from Ramdev ji. How do you explain frustrated magnetism?
Frustrated. I told na there is a triangle is there. One spin is up, another spin is down. Third one where it will go. Then there will be frustration will come.
Sir, question from Rehana Naz. What is the synthesis of organic nanomaterials?
There is a chemical method. Organic nanomaterials, we will make it through chemical methods, solution methods.
Sir, a question like from Prashant sir.
Okay.
Superconducting material is there at normal temperature? If yes, then which are that?
Still not it.
Sir, these are from chat box, sir.
Sir, can I have some doubts, sir?
Okay, no problem.
Can I ask, sir?
Yeah, why not?
So, how to identify the polymerism in specimen? So is there any technique like XRD, TEM, etc.? As you say that the space groups are different.
Yes.
So are you prepare the sample and cut the surface and bulk material, take the XRD, or is there any technique? Is there?
No, actually, I just whatever I got a crystal, I just kept in a X-ray machine. Then it will give you the single crystal X-ray. So only few peaks. Okay.
Okay.
So what I told that MOTE2, the both are similar.
So,
is it
like
not? But only thing is
say
the
that the surface has some and bulk has some other spaces. So as you say that topological materials having the like different crystal structures,
conducting and non-conducting,
like arrangement of atoms are different in sets. How could we know this? Like, is there any technique?
That is ARPAS, no? That is I told that is ARPAS. There is a one instrument, so we can calculate the band gap.
Yeah. Okay. And one more doubt, sir. So what about density of states at surface and core? Is there a density of state changes according to the position within the material?
Of course, of course. So we calculated, na? Some of the calculated, na? Density of states also similar like valence band, conduction band, na?
No, as you say that surface having the conduction and bulk having the insulator means density of state should be different at different positions, different spots.
Yes.
So is it true, sir?
Yes, it's correct.
Yeah.
They calculated according to that.
Okay. So as I know that like density of state at room temperature is constant, but as you say that the density of state changes according to the position within the material.
Yes.
Is there band
not
gap
all materials, only few materials?
Yeah, topological insulators. Is there band gap changes with material? Same, na? Same.
Of course, na? Band gap almost it will change.
Changes. Thanks a lot, sir. Thanks a lot.
Any other?
Sir, I have one question.
Okay.
Sir, this CVT, chemical vapor transport, you mentioned.
Yeah.
So at what temperature this become a vapor?
It depends on the material.
No, this molybdenum telluride.
Molybdenum telluride. So I use tellurium bromide. Okay. So tellurium bromide, it will dissociate around 450 degrees centigrade.
Okay.
So that means you required above 450 only, you will get that MOTE2.
Okay. And this is a CVT method. Is it you did in a reactor or what is that?
That's means a 3-zone furnace, normal furnace.
Normal furnace. Okay.
Yeah.
Okay.
Normal furnace with quartz evacuated quartz tube.
Yes.
But I told that.
Yeah.
That's it.
Okay. Because there is a PVT is also there, physical vapor transport.
Yes. PVT also there.
So there you can get 4H and 6H.
Yes.
4H and 6H materials.
Yes.
Silicon carbide.
Yes. It depends on how the material, how we can, it will be vaporized or not, like that. Depends on that, you can choose the method. That's the processing method, na?
Yes.
The first condition itself that, the processing condition and performance, structure and property. These are the 4 parameters.
Yes, sir. Very nice presentation, sir.
Thank you.
Sir, next question from Ramdev. I request Ramdev ji to unmute yourself. I have given permission. Please unmute yourself and ask question.
Good afternoon. Good afternoon, Ramdev.
Ramdev, stop. You can ask a question now.
Good afternoon, Ramdev.
Hello?
వీడియో పెడితేనే వస్తాడేమో.
వీడియో పెట్టుకోవచ్చు. రామ్దేవ్. హలో
Any
Hello,
other?
Ramdev, are you there? Allah,
ఉన్నాడు ఉన్నాడు
Ramdev.
ఉన్నాడు ఉన్నాడు ఉన్నాడు.
Okay. Ramdev?
I think he
Hello?
may not be there, sir. His bandwidth is very low, sir. So I think he may
Okay.
not get connected, sir.
Okay, okay. So he typed any question?
No, sir, not yet, sir.
Okay.
For that reason, I am asking on behalf of them. I will be asking so that
Yeah,
because
yeah.
bandwidth is very low, sir.
Yeah, yeah.
If they
Yes,
connect
yes.
also, they cannot speak, sir.
Yeah. That's true.
Hello. Thank you, Dr. Narsingh Rao.
My
So
pleasure.
now I request Ankam Bhaskar to speak.
Yeah, vote of thanks. Honorable Vice Chancellor and Registrar, respected Speaker, faculties, and all the participants, I consider it is a great honor and privilege to propose a formal vote of thanks. I would like to thank all organizing members, faculties, and all the participants for attending this seminar. Our speaker is explained a few important topics, important points. Classification of materials based on the band gap, classification of materials based on the spintron, topological insulators, and edge of the material and surface of the material, resistivity, specific heat, magnetic property, and superconductor properties of topological materials, and low dimensional magnetic in 1D, 2D, and 3D materials, and applications of polymerism materials. The way in which he explained his topic was extraordinary. I'm sure that all the participants who take note of important points during his lecture. On the behalf of our department and all the participants, extend a very hearty vote of thanks to Honorable Delegate who blessed us with his presence and took out valuable of his time even though he is busy. I would like to thanks once again for making this seminar as a success. Thank you, sir.
Thank you.
Thank you, Bhaskar.
Thank you, Anna.
Okay. So once again, I will thank the Registrar of Palamuru University, Professor Pawan Kumar, OSD, to Vice Chancellor Dr. Madhusudan Reddy, and Principal, University Peak College, Palamuru University, Nutihar, for their encouragement in organizing this program. So I deeply express my sincere gratitude and appreciation to the speakers, Dr. Y. Purushottam, Dr. G. Narsingarao, for accepting our invitation and having shared with us their knowledge and experience. They have taken time out of their busy schedule to contribute to this program. Thank you for your valuable contribution and sparing the time with us. I thank my entire team for all efforts they have put in to make this program a success. I thank all the participants from various institutions who have attended this program, without whose presence this program would not have been successful. So it's a special thank to Dr. Arjun for his technical support since day one of this program initiation and ensuring that things to materialize. I would like to thank everyone present here. Thank you, one and all.